When you look up at the night sky, it offers a beautiful, profound, and utterly misleading sense of scale. From our vantage point here on Earth, the pinprick of light that was once the planet Pluto and the faint glimmer of the star Proxima Centauri can seem like neighbors in the cosmic dark. Yet, they represent two vastly different scales of difficulty for human exploration. Reaching Pluto, a journey we have accomplished just once, was one of the crowning achievements of planetary science. Reaching Proxima Centauri, our nearest stellar neighbor, remains firmly in the realm of science fiction. The gap between these two challenges is not just a simple matter of a longer journey, it is a fundamental shift in physics engineering and our very definition of what is possible. We have now sent probes to every classical planet in our solar system. We have rovers diligently crawling across the surface of Mars and a magnificent observatory, the James Webb Space Telescope, that peers back to the dawn of time. These triumphs might lead you to believe that the cosmos is our backyard, ready to be explored. However, the mission to Pluto served as a stark and humbling reminder of the true scale of our own solar system. It was a journey of billions of miles, a masterpiece of planning and precision, and yet it was only a flyby that lasted a few precious hours. This single fact, that our best effort to reach the edge of our own planetary neighborhood resulted in a brief, one-time glance, is the key to understanding the profound challenge of interstellar travel. Pluto is, in astronomical terms, just next door. Proxima Centauri is on the other side of an ocean of emptiness so vast that it requires a complete rethinking of what a spacecraft even is. The physics that got us to Pluto breaks down when applied to the stars. The engineering solutions we devise for a 9-year trip become utterly irrelevant when the journey is measured in millennia. It is a difference not just in degree, but in kind. So, why is this? Why does a journey to a dwarf planet at the edge of our solar system feel like a leisurely stroll compared to the impossible marathon of reaching the next star over? The answer lies in a series of cascading physical constraints that begin with a surprisingly simple, yet deeply unforgiving, principle of rocketry. It's a principle that governs every single spacecraft we have ever launched, from the first Sputnik to the most advanced probes. At the heart of our struggle to explore the cosmos is a concept called the rocket equation, and you don't need to know the mathematics to feel its weight. In simple terms, it describes the relationship between a rocket's fuel, its mass, the final speed it can achieve. The logic seems straightforward. To go faster, you add more fuel. But the equation reveals a cruel twist. That extra fuel has mass, which makes the entire spacecraft heavier. A heavier spacecraft requires even more fuel just to get it moving, and that additional fuel adds even more weight. This creates a cycle of diminishing returns that quickly becomes overwhelming. This isn't linear, it's an exponential one. Doubling your fuel does not double your speed. To get small increases in velocity, you need disproportionately massive amounts of propellant. It's like packing for a very long hike. The team that designed the New Horizons mission knew they were trapped by the rocket equation. Launching a probe with enough fuel to fly directly to Pluto and then slow down to enter orbit was simply impossible. The required spacecraft would have been too heavy to launch with any rocket available, so they did something far more elegant. They decided to steal speed from a planet. This maneuver, known as a gravity assist or a gravitational slingshot, is one of the most brilliant and counterintuitive tricks in the celestial mechanics playbook. It allows a tiny spacecraft to gain an enormous burst of speed for free, without burning a single drop of fuel. Here's how it works in principle. Imagine rolling a tennis ball past a moving truck. If you time it just right, the ball doesn't just get deflected by the truck, it gets caught in its wake and is flung forward with more speed than it had when it approached. The spacecraft does the same thing with a planet. As New Horizons approached the giant planet Jupiter, it fell into its immense gravity well. Jupiter's gravity pulled the probe in, and because the probe was aimed carefully, it swung around and was thrown out the other side. In the process, it stole a tiny fraction of Jupiter's immense orbital energy, translating it into its own velocity. The boost was spectacular. 13 months after launch, New Horizons flew past Jupiter, and its speed jumped by a staggering 9,000 miles per hour, about 14,500 kilometers per hour. This single maneuver shaved 3 full years off its journey to Pluto. Without Jupiter's help, the mission would have taken nearly 13 years instead of 9.5. It is a genuine case of getting something for nothing, a free lunch provided by the laws of physics. Jupiter's orbit slowed by an infinitesimally small amount, a change so tiny it's effectively immeasurable, but that was enough to change everything for the little probe. Of course, this cosmic gift comes with a condition. Timing is everything. To perform a gravity assist, you have to arrive at exactly the right place at exactly the right time. The launch window from Earth for New Horizons was incredibly narrow, calculated so the spacecraft would cross Jupiter's path when the planet was perfectly positioned to fling it toward Pluto. Arriving at Pluto presented 2 more problems that are less about speed and more about the sheer emptiness of it all. Power. Communication. Here on Earth, we take the sun's energy for granted. But as you travel away from it, its light and warmth fade dramatically. At Pluto's average distance, some 3.7 billion miles away, the sun is nothing more than an intensely bright star in the sky. The sunlight that reaches Pluto is about 1,000 times weaker than the light that reaches Earth. For a spacecraft, this means that solar panels, the workhorse of missions in the inner solar system, become all but useless. You simply cannot run a sophisticated suite of instruments on such faint light. This is why probes destined for the outer darkness carry their own source of power. New Horizons. Voyager spacecraft. They use a device called a radioisotope thermoelectric generator, or RTG. An RTG is essentially a nuclear battery. It contains a lump of a radioactive element, typically plutonium-238, which naturally gets very hot as it decays. This heat is converted directly into a steady, reliable flow of electricity. The power output is modest. New Horizons had about 200 watts to work with at the start of its mission, less than what you need to run a couple of old incandescent light bulbs. Every single system had to run on this tiny power budget. Heaters, cameras, transmitter. The second problem is the sheer time it takes to talk to a spacecraft so far away. Radio signals, like light, travel at the fastest possible speed in the universe, approximately 186,000 miles per second. But even at this blistering pace, the distances are daunting. When New Horizons was at Pluto, a command sent from Mission Control on Earth took 4.5 hours to reach it. The spacecraft's reply, confirming it had received the message, would take another 4.5 hours to travel back. This 9-hour round-trip delay makes real-time control impossible. You can't joystick a probe at Pluto. This communication lag fundamentally changes how missions are run. Every sequence of events for the Pluto flyby had to be meticulously planned, programmed, uploaded to the spacecraft's computers, days or even weeks in advance. During the most critical hours of the encounter, as New Horizons flew past Pluto's moons, it was completely on its own. If an unexpected problem had occurred, there was nothing anyone on Earth could do about it. The probe had to be autonomous, intelligent enough to follow its complex sequence of instructions and handle any minor glitches by itself. It was a lonely, robotic vigil in the cold and the dark. The journey to Pluto, for all its difficulty, was still a journey within our own cosmic home. Proxima Centauri is something else entirely. It is the closest star to our Sun, a small red dwarf star, orbited by at least one planet we know of. Yet, close is tragically misleading. It lies 4.24 light-years away. A light-year is the distance light travels in a year. That's about 5.88 trillion miles. So Proxima Centauri is about 25 trillion miles, or about 40 trillion kilometers. This number is essentially meaningless to our human brains. It's a distance not of miles, but of lifetimes. Let's try to put this in a more familiar context. Voyager 1 is currently the fastest and most distant object sent from Earth. It is hurtling through interstellar space at about 38,000 miles per hour. That's about 61,000 kilometers per hour. If, by some miracle, Voyager 1 were aimed at Proxima Centauri, it is not. It would take approximately 76,000 years to arrive. Recorded human history, from the first writing in Mesopotamia to today, spans only about 5,000 years. The entire agricultural revolution happened about 10,000 years ago. Voyager's journey would be more than 7 times longer than that. This is why conventional propulsion, the kind that got us to Pluto, is not even part of the conversation. Chemical rockets, solar sails, ion engines, they simply do not provide the necessary speed. To make the journey to Proxima within a human lifetime, say 50 years, a spacecraft would need to travel at roughly 10% of the speed of light. That's an astonishing 67 million miles per hour. We have never built anything that has achieved even a fraction of 1% of that speed. The gap is not incremental, it is a chasm. The communication delay also scales up to an absurd degree. At Pluto, the 9-hour round-trip time for a signal was a major operational challenge. At Proxima Centauri, one way is 4.24 years. Another 4.24 years back. That's nearly 8.5 years between asking a question and receiving an answer. It transforms a mission from remote-controlled operations into something like sending a message in a bottle and hoping for a reply decades later. The very nature of scientific exploration would have to change. To cross the interstellar ocean, we must abandon the chemical rocket. The physics is clear, we cannot carry enough fuel to get there. Therefore, the solution must be to build a spacecraft that doesn't need to carry its fuel with it. Several radical propulsion concepts have been proposed. One of the oldest and most dramatic ideas is nuclear pulse propulsion. First studied under Project Orion in the 1950s and 60s, the concept is brutally simple. Detonate small nuclear bombs behind your spacecraft. The shock waves push the ship forward. Later studies, like the Daedalus project in the 1970s, refined the idea. Daedalus envisioned a colossal 2-stage vehicle. Thousands of nuclear pellets detonated over several years, accelerating to about 12% of light speed. Fast enough to reach a nearby star in roughly 50 years. But the engineering is monumental. The craft would weigh tens of thousands of tons. International treaties banning nuclear weapons in space are a political hurdle. It is brute force, yet one of the few concepts that could reach the necessary speeds. A more elegant and modern idea is the laser sail. The craft is an ultra-light, highly reflective sail with a tiny payload. The engine stays behind as a massive laser array. The array focuses an intense beam onto the sail. Photons exert gentle, continuous pressure to push it. No onboard fuel means huge accelerations are possible. This is the principle behind Breakthrough Starshot. Starshot aims to accelerate gram-scale probes, postage stamp-sized, to 20% of light speed. At that speed, Proxima would be about a 20-year journey. Data return would take another 4 years. Potentially, our first close-up look at another star system within one human generation. The challenges are enormous. Building a 100-gigawatt laser array, designing a sail that can survive that energy, protecting a tiny probe from interstellar dust. Still, a physically plausible path forward. Getting a spacecraft to 20% of the speed of light is an almost unimaginably difficult problem. But there is another problem, one that is almost never discussed, that is equally hard: slowing down when you get there. In the friction-free vacuum of space, an object in motion stays in motion. Once you turn off your engine, you will coast at that speed forever. This is wonderful for the long cruise between stars, but it means that to stop, or more accurately, to decelerate into orbit around your destination, you must perform a braking maneuver as powerful as your initial acceleration. For a mission like Breakthrough Starshot, stopping isn't part of the plan. The tiny probes are designed as flyby missions. They will scream through the Proxima Centauri system at 20% of the speed of light, snapping as many pictures and collecting as much data they can in the frantic few hours. Then they will continue onward into the void, their one-way journey complete. This is the interstellar equivalent of the New Horizons flyby of Pluto, but sped up by thousands. It is incredibly valuable science, but not the same as a true exploratory mission. For any mission that aims to orbit land or carry human passengers, the deceleration problem is catastrophic. Under the tyranny of the rocket equation, needing fuel to both speed up and slow down makes your fuel needs explode. It doesn't just double. The mass of fuel becomes so astronomical that it renders the entire mission impossible from the start. It is the ultimate cosmic catch-22. To arrive, you must carry the means to stop, but carrying that means makes you too heavy to ever get there. This is the great, quiet filter of interstellar travel. It separates a flyby from a true arrival. Perhaps future engineers will devise a way around it. Maybe a spacecraft could deploy a magnetic sail to brake against the destination star's stellar wind, or use its laser sail in reverse to catch the star's light. But for now, it remains a monumental challenge. These limits are not failures of imagination, but honest reflections of the physics of our universe. They teach us humility and clarify the scale of our ambitions. Knowing how hard the journey is the first and most important step toward one day figuring out how to make it. We are not at the beginning of this story. We are somewhere in the middle of it. The numbers will permanently change how you see the night sky.